Beautiful. Oh, I didn't start up the PowerPoint. Duh. maybe we should have waited a little while. Okay, performance. Why worry? So tonight, why worry about performance? Well, I use the terminology performance tuning, and I'm going to talk about performance not from a programming point of view, like how do I increase my program's performance. I'm going to talk about performance at the database level, which basically involves SQL statements. Now, at the start of the semester, week 1 or week 2, I forget where, but I gave you some horrible looking SQL statements as a sample. Yeah, that different students have gave me over the years and I've picked up from my experience and so on. So often SQL statements are massive in size because we try to do as much as possible to create a report or do, as I'll talk about a little bit later on. And it's those sort of statements, when we develop those, and they're not developed in a day or an hour, they take a long time. And then we basically look at those SQL statements, we do what's called an explain plan, and we analyze to see how they perform, how well they perform. And I'll talk about that explain plan and the measurements of performance and try to explain that so you have some idea of what's going on and what the developers or database people get involved with and the sort of terminology they use. Performance considerations start at the design stage. So we'll talk about how SQL is processed. We'll talk about the optimizer, the cost-based and the rule-based. Rule-based, I believe, is sort of becoming a little bit obsolete and is primarily the cost-based optimizer. I'll talk about what an optimizer is. I'll talk about indexes and what is an index. Plan table, well, we'll talk about that, but that's old hat now because we've got tools like SQL Developer and so on. Writing efficient SQL and writing performance efficient PLSQL. I'm not going to talk too much about that, but I will make a point as I go through of some of the way that students think and what I've seen over the years and even this year. And I may embarrass a student in a class, but look, if I do, my intention is not to embarrass you. I want to use the experience that was presented to me to illustrate to the rest of the students, how you shouldn't think or should think. Why worry about performance? Let's think now. A user is interacting with a customer, and this is what basically happens. So, you get a call center, wherever the call center is, it doesn't really matter. The user wants to appear intelligent, efficient, and above all, they want to help the customer or somebody at the other end. And that person at the other end is working on a computer, and they may be working on your program. So when they're talking to the people, they want to sound intelligent, they want to sound efficient, and when they press the buttons, the system should be responding back. Not, I don't know how many times you hear the situation when you are talking to a call center, oh, geez, the computer's slow today. You hear it all the time. Now, that's lots of reason for that, but one of those things is software. Now, in order for the people at the other end of running the code, what they need to do is they need an application to allow them to work smoothly. So the flow of steps that are performed are smooth and intuitive, and the response time is to be appropriate. It is not appropriate to have a customer waiting while the system searches for their data. So they might say, oh, what's your name? Benkovic, it's too hard to spell. What's your phone number? You don't want the person at the other end to say, what's your customer number? What the hell do I know? So basically they'll say Benkovic, B-E-N-K, and as they type in, the person's listening at the other end, but as they're typing information in, bang, 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 things are happening on the screen. That's what we want. An application and a database will need to be tuned to cater to the needs of the user, and the user are the ones running your program. In a database environment, we often have batch processing. Data warehousing is very, very big now. This is where the reporting comes in. What often happens is that we have what's called mission critical systems. Could be our payroll system, could be our processing system, you know, the system where orders are taken and dispatched and so on. Those systems are generally not used for reporting because they are there for one and only one purpose, and that's to do whatever they have to do. Often what we'll do is we'll download the data from the mission critical systems down wherever, and they usually end up in some data warehousing area somewhere. The data is diced and processed and so on, and this is where the reports come in. What's the usage of our terminal? Which is the most profitable? Which is the least profitable? How many terminals do we have at a particular area? Yeah. All these sort of questions that financial people want answered in order to increase their profitability. Certainly one of the aspects of it. They may be now in a database environment. We have batch processing that could happen after hours. In data warehousing, batch processing again. In those sort of environment, there may be many jobs running either in parallel or sequentially. There is definitely potentially hundreds of jobs that are being scheduled and they run. They either run in parallel or sequentially. Sometimes a job depends on a successful completion of a previous job, and the next job can't start before the previous one is finished. So all those processes that are dependent, if they're running in parallel, different processes are running. They could be occupying the processor and taking up resources from the machine. It may be in some systems that at a certain point in time, particularly with databases, the database might shut down at, let's say, 2 o'clock, and there's a backup that happens from 2 o'clock, and the backup usually takes, let's say, 2 hours and so on. So from 2 o'clock to 4 o'clock, if it's an older system, you know the database has got to be shut down and nothing happens. So the jobs need to be scheduled. Once the backup finishes, maybe another job will then start off, and our settlement system could kick off, and then the settlement system could then create files in the operating system, and there'll be something else picking up those files and sending it off to who knows where. So all that processing, all that work that's happening behind the scenes, so that when the users come into work in the morning, bang, everything is ready for them. It is not appropriate that reports are not there. It is not appropriate that the system fails and something is not produced, because this is how companies go out of business. I said to you at the start of the year, we'll see what happens this year from a system software failure. I think we've had Coles that failed in the last couple of weeks. The airport failed on a couple of occasions. I think something happened with the scheduling system with the airlines, didn't they? There's been a few little episodes where things have failed and they become very, very costly. The PR people get onto the radio and everything. Oh yeah, everything's okay. We've looked into it. But can you imagine what's happening behind the scenes? When the airport clogs down, imagine the traffic in a city. It affects not only the airport and the system, it affects the country in a lot of times. Not to mention writing software for a moon lander that all of a sudden gets there and then, we lost connection, which I think happened to one of the missions, wasn't it? Billions of dollars down the drain because what was somebody forgot to swap a time interval or something really, really stupid, and I laughed anyway. So reports may be needed before start come to work. So these are the sort of issues that revolve around a database, and not one person and not one entity is responsible for all this. There's people working in those sort of environments that are like ants. They all have their roles and whatnot. But often, as developers, we have to start understanding that we are often writing code which potentially could be critical. If not writing code, we're certainly supporting and maintaining that code. Performance is really an issue in small databases because the volume of data can easily be handled by the hardware. We have CPUs now, you blink and the thing works out what has to be done. In large databases, just before I go on, can I have hands up of people who have got their code running? Just hands up so I can get an idea. Doesn't matter what they do, is the code running? Is anybody's code taking any more than 2 or 3 seconds to run?
Crash.
Well, crash is a bad thing, but not a time. Any more than 2 or 3 seconds to run. Oh, that's good. Because, in the years gone by, every year in this assignment, I'll press enter. I see the lag, like it might take a half a second, some of them take 3 or 4 seconds, some take 4 or 5 seconds. This is one of the things that I judge performance, because I'll see straight off. You should be able to press the button, bang, the system should finish, no matter what it's doing. If not, things that are, and I'll talk about that in a little while. Small databases, performance is rarely an issue. In large databases, the issue of performance and response time becomes one of critical components of an application. Often the performance of an application may be satisfactory at the start. I'll tell you the story about my friend Danny Delan, who was the best developer that I ever met. Often the performance of it may be satisfactory at the start, but as the data volumes grow, it often happens that performance degrades and degrades and degrades. Programmers then need to get involved to try to fix the problem. So the users complain, look, this is taking longer and longer and longer. The programmers get involved, says, okay, how are we going to fix it? There is no magic bullet, unless it's something really stupid. If performance was considered at the design stage, then the problem would be anticipated and catered for. One of the first things that you as a developer, depending on what sort of system you're working, but this is a database environment, one of the first things that you will need to address, or your team leader, which will be you in a couple of years, you'll need to address what is the data volume of our system. And what is our response time? And then you might say, oh yeah, we're going to start off with 100,000 records. But how soon will we get to 1 million records? Do we have disk space? Do we have this? Do we have that? Do we have that? And the next thing is, when we write in code, we need to understand that we've got massive volume of data. How are we going to address it? So this is all considered at design stage, not, oh, the program is starting to run slower now, let's go in and fix it. Because it might mean a rewrite. Because the developer has written some crap because it works for him, but she never considered the data volumes in the future and how the system will handle it. How is SQL code processed? SQL is a relatively easy language to learn. It's non-procedural nature, so there's no procedure. You just basically tell SQL what you want, not how to get it. So its non-procedural nature tends to obscure performance-related issues. As a result, it is much easier to write functionally correct SQL than it is to write efficient SQL. SQL has been designed so you say what you want, rather how or where you get it. So when you say select star from table terminal, table customer, table transactions, enter, you in your mind are looking at the syntax. Does it work? It works. Fantastic. Have you ever considered how SQL is processing the data? Have you ever considered looking at the volume of your data? Have you ever considered that maybe you'll put the table with the lowest volume first, and or maybe even the table with the highest volume first in a list? Does the order matter? Does the order of your attributes in your select statement matter? Have you ever considered that? My guess is no. But hopefully after tonight's lecture, you'll see that, not that you'll consider it, but you'll say, oh, hang on, this is a little bit more complex than I thought. Now, to achieve this, SQL, gives you what you want, you don't have to tell it where to get it. To achieve this approach, the database management system must support a very sophisticated algorithms to determine the optimal method of retrieving the results or processing the modifications. In most cases, these algorithms are collectively referred to as, and you'll hear the term, and we'll talk about the term tonight, the optimizer. So every database has an optimizer to optimize your SQL code. So, and this is just a set of algorithms and procedures inside a database that's built in. So there's not one thing that says, oh, this is the optimizer. There's algorithms and procedures, and collectively that's called an optimizer. For almost all SQL statements, there will be more than one way to retrieve the rows required. When the database management system passes the SQL statement, it must decide which approach will be the fastest. The process of determining this optional path to the data is referred to as query optimization. So there's another terminology, query optimization. So you write a query. Now also think not so much about your little statements with 2 or 3 lines, but think of those SQL statements that I gave you at the start of the year. How does the database system decide, or you as the developer who writes the SQL decides that this is the way you write the code which will be the most efficient? Because some of those SQL statements could take hours, days to run, depending on the volume of data. So query optimization is very important, and we as developers writing reports and writing SQL queries and so on will need to consider query optimization, and we will use the tools offered by the optimizer. Oracle, as with most database systems, have two, most of them support 2 approaches to query optimization. You'll hear the terminology a rule-based optimizer and a cost-based optimizer. So when you're talking about performance tuning and all that sort of stuff, they'll talk about rule-based optimizer, cost-based optimizer. Rule-based optimizer, thank goodness, is slowly phasing out, and it all comes down to cost-based optimizer. I haven't looked for a while, but certainly when I was looking at Link and Seek and looking for whether we're advertising for database developers, almost always, without exception, must have experience in query optimization or performance tuning, must be capable of performance tuning. So it's a very good skill, or it's a mandatory skill to have, and it's something that you will have to develop. Anyway, optimizers. Query optimization, and when we talk about optimizers in a database, there are basically 2 types, rule-based optimizer and a cost-based optimizer, no matter what the system is. A rule-based optimizer, you can read this for yourself, and I'm sort of sounding like a parrot reading this sort of stuff, so I'll explain it in my words. When you write a SQL statement, and particularly in your where clauses and the order of your table, no matter what happens if the system is using a rule-based optimizer, if you put for example, if you put tables in the order from FFS terminal, FFS merchant, FFS transactions, the order that you put the table, the rule-based optimizer might say, okay, I'll process the first table, then I'll process the second table, then I'll process the third table, irrespective of the data volumes. So the rule-based optimizer will always follow a set of rules to achieve its end result. It doesn't really look at how much something costs. Yeah, so rule-based optimizer will almost always follow the same path. Now, you might swap the from clause and say from FFS terminal, FFS merchant, FFS whatever, and then the system will still follow the first table, second table, third table. Even if you change your query, the system will always follow whatever the rules are. And I use an example of the table ordering and processing those tables as a very trivial example to hopefully, try to sort of illustrate. But the rules are much, much, much more complex, as you can imagine. The cost-based optimizer will always make its decision based on the statistical information relating to the volume and distribution of data within the tables and within the indexes. In a cost-based optimizer, and nowadays certainly Oracle almost exclusively uses the cost-based optimizer, tables, indexes, and we'll talk about indexes in a little while, contain statistics apart from the stuff that I showed you, with its name, what the attributes are, and the attribute data types, and so on. There are how many rows are there? What's the highest row? What's the lowest row? Does it have an index? Does it have this? Does it have that? How many records? Etc. 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 Now, all those statistics, the optimizers calculate. They look at your SQL query. They break it all down, and they use the statistics that are stored in the database to calculate our cost, our number. And let's say that number is 100. Don't worry about what 100 represents, but the number is 100. Now, what the optimizer will do is it look at your query and say, okay, what if I do this, what if I do this, what if I do this, and what if I do this? And from the statistics, it will calculate a cost, a number. And if that number is 200, then straight off the optimizer says, oh, the 100 is cheaper if I adopt this strategy to extract the data. It's better than this strategy, which is costing 200. And it goes through and it does all these permutations, the calculations. This happens every time you press enter on your SQL statement. The optimizer goes away and works it out. Now, our queries are nothing. Yeah? But they can. A lot of the SQL statements are very complex. So the optimizer basically works out, and it's the optimizer works out the cheapest cost. Now, indexes and so on are concerned in here, and we as developers, we need to take a little bit of a look at how we create the underlying structure. We have to be proactive in updating our statistics and so on, but I'll talk about that in a few more slides. So cost-based optimizer, rule-based optimizer looks at the SQL statement, has a set of rules, follows those rules no matter what the data volume or distribution of the data is. Is one table got more than the other? Same rules, and basically executes the query. Cost-based optimizer every time looks at the statistics of the tables or the data in the tables and then statistically works out the cost. How that's done, don't worry, who cares? That's what the big Oracle developers and so on get paid to work out. And as I say, the number, it's not a cost like it's in dollars and cents, or processing cycles, a number that works out a number, and then it compares those numbers. The statistical information is not, so a point to consider, something I want you to take away. When you create a table and you're putting data in, you're dropping data, you're deleting data, and so and so. The statistics are not automatically generated. It should be updated regularly so the optimizer can make valid decisions. So you guys, if you were to go through and you're downloading data into your transactions table, the transaction table will grow. In your code, somewhere along at the end, when it's all finished and you're updating the data, because there's obviously a process that brings the data in, one of the commands would be gather statistics. Now, you don't do this, but in a real world, we would update the statistics. Because as the data volumes grow, or there could be another process which is archiving data, which data volumes could be shrinking, or old data is being removed. Things are changing. Everything's volatile. And those changes have an effect on the statistics of that table. Those statistics are not automatically generated. This is we developers need to do that. Or do that, and often what the DBAs, but the DBAs, what do they know? They don't know what the volume of the data is. They don't have a database. We will potentially schedule some statistics gathering software during the night to run out of hours, when it's not interfering with something, because it does take some resources. The cost-based optimizer is far superior to the rules-based optimizer. Now, consider this query. If you can't read it, select distinct customer name from customer order table employee, and joining the employee number, the employee table, joining the customer table to the customer to the order table, and then looking for an employee called Landy Santos, and looking at the situation where all date is greater than CSTAT minus 357. So we're looking at the orders in the last 12 months. Simple, yeah? Fairly straightforward. Now, the above question, so this query says, give me the names of all the customers who bought something from sales rep Santos in the past year. There's the SQL statement, there's a request, SQL statement. How do you solve this? One, and again, I'm going to read this for you. Get all the sales for the past week. Then get the names of all the customers matching those sales. Then filter out all those customers not served by Santos. Okay? Get Santos employee ID. Using the ID, get all the customers handled by him. Then filter out all the customers who haven't bought anything in the last week or the last year. That's an approach. Get all the customers, filter out all those who were not served by Santos, then filter out those that haven't made any purchases. 3 valid approaches, and it could be more if you look at it a little bit. Which is the best? Which is the most efficient? Now that's what the optimizer has to decide. You are so concerned about writing syntactically correct code to produce an answer to this question, and now the database has to decide, how am I going to do this? A rule-based optimizer will always pick one of the rules and always follow that sample. Cost-based optimizer will look at the tables, look at the statistics, data volumes, operations, and then depending on what is cheap, do a comparison between these 3, not actually executing the query, but mathematically working out the cost of each query and pick the cheapest one. And it could be, as the data volumes change over time, it could be that they could have different approaches in a cost-based optimizer. The rule-based optimizer will always take the same approach. That's the difference between the two. And this is why the cost-based optimizer is far more efficient. In order to execute the query, the rule-based optimizer will always, that's what I just said. Now, the path will be determined by the rules set up in a database. Use indexes if one exists. So, if we put an index on a table, and I'll talk about that, if we put an index on a table, the rule-based optimizer might say, well, if there's an index there, I'll always use it. The cost-based optimizer might say, hang on, if depending on the data volume and depending on the uniqueness of the field that I'm looking for, it might be quicker for me to go to the table rather than go to the index and then go to the table. Yeah? So these are the sort of decisions that the optimizers make. The cost-based optimizer will calculate the best access plan. The calculation will be based on the statistics that are stored in the database. As the data volumes change, the statistics need to be updated, accurately reflecting the data volumes. Now, I used to have a software called Toad, but I don't have it anymore because that cost about $2,000 or $3,000. But in Toad, it had a fantastic little tool where you could go through and look at the statistics of a table. You know, the developer could look at it, and then we would go through and then update the statistics on a table, and then we'd look at it again and see how it's changed. Now, this is just a screenshot, and for me to talk about is that this. Look at the metadata. So, if you look at the all tables and look for a particular table, in this case FFS transaction. Remember, all tables is an object that provides all the details, all the metadata about data for the tables. So all tables, if you look at the table name FFS transactions, it'll come back and tell you, average row length, average spaces, degree, cardinality, yada, 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 the size and all that sort of stuff. So this is where all that information is, and this is the statistics that the optimizer uses. So the metadata. We have a package called sysdbms. I don't want you to use that, so you can read this at your leisure. But there are no doubt there are packages in a system, in all database systems, where you run them to gather statistics and bring information up to be the most current. I'm going to talk about indexes. So that's an overall of cost-based optimizers, rule-based optimizers. And then when we have a whole lot of data sitting in a database, consider this. Consider if I said, let's say your transaction data, and your transaction data is based on terminals, yeah? So if I said to you, give me, select blah, blah, blah from FFS transaction where terminal ID is equal to blah, and you're the optimizer, what will you do? How will you get that data from the table? If it was me, I'd go to the top and I'd look. Yes, 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 no, yes, no, yes, no, yes, yes, yes. If it's yes, I'll bring the record out. Yeah, bring it out. But I'm going through and I'm looking at every record. Now, if there are 1 million records, how many times do I have to look? 1 million times to get all the data. My terminal, there are many terminals, but imagine if it was a primary key. My terminal, or the data I'm looking for, could be the first, bang, instant. But it could be the last. So I'm going through 1 million times. Why do I need to do that? Because I need to do that because the data's not ordered. If it was ordered, I could do a different search pattern, yeah? And this is where indexes come in. So what we do is, if we have tables with large volumes of data and we are joining or we are searching on particular fields, what we often do is we put indexes on those fields. Believe it or not, when you create a table and when you choose a column to be your primary key, guess what the system does? The first thing that it does on that column with the primary key. Have a guess. Seeing that we're talking about indexes. It creates an index. And guess what that index, what happens to that index? Or no, what's the main property of an index? It's ordered from one to the end, whereas normally we could have data stored in the database in any order. Because remember, some of the properties of your, what's the term they use in database fundamentals? Not a table, entity. A property of an entity is the data, the column order is immaterial and the row order is immaterial. The system will look after it, yeah? But anyway, I digress. So tables with large data volumes require considerable resources to find a single or a group of records needed. The easiest way to speed up access to these tables is to create an index. Index has a schema object that exists primarily to enhance performance. Now, primarily to enhance performance. Understanding and using indexes effectively is therefore of paramount importance when optimizing SQL. Paramount importance. I'm surprised that we don't teach you indexes before this, but indexes are of paramount importance in database systems, especially big database systems. Effective indexing can result in huge improvements to SQL performance when searching for a record. When I say it could be huge improvements, it could also be a handicap if deleting or inserting or updating. And I say do a bit of a discussion. But before I discuss, I need to tell you what an index is and what it looks like. How an index is implemented. Most large databases use a B-tree structure. I might come back to this, and I'm going to go over here. Now, in your previous studies, have you done a B-tree? Have you done B-trees? Oh, you've done these, haven't you? Of course you have. I think in year 1, didn't you? Binary trees. Yeah, B-tree. You know this. So basically in your, and I think you did it with your linked lists, or you would have, where basically you turn around and you put a record in there, say 12. And then next thing you put in number 17, so the system goes in, is 17 greater or less than 12 or greater than? So I go into the right-hand path and put the number down. Next I'm going to put 7 down. Is 7 less or greater than 12? Okay, 7 is less, so I go on the left-hand side, put 7 down. Right, so the numbers are in. 24. Is 24 less than 12? It's greater than. Is it less than or greater than 17? Greater than. Go to the right-hand side. And so on. And what happens is the system builds a B-tree. Binary tree. Binary means 2. Okay? Always 2. Always 2. So, if I had a table, if I had just a table somewhere, and I had those numbers in there, and if I'm looking for number 11, yeah? And if I go through and searching, I'll say, is it? Ah, got it. 1, 2, 3, 4, 5, 6, 7. 7 hits. Yeah? Imagine that's 1 million. If I had a B tree, then I can say I'm looking for 11. Oh, 12. Is it less? No, over here. 7. Is it more? 11. 1, 2, 3. Binary tree. What's the problem with binary trees? They can easily be a sequential number, so they don't offer you very value. B tree, binary indexes, what database systems use is they use what's called B tree indexes, but B doesn't stand for binary, it stands for balanced tree. I'll explain that. Now, what happens with database systems is they use B tree indexes. The binary tree I used to explain, but in the balanced tree, what the system does is it has a data type, and in the data type, what they do is they store a range of values. So if you're creating an index and you're looking for a customer ID, they'll say from 1 to 1,000, it belongs here. Go start looking here. From 1,001 to 5,000, look there. From 5,000 to whatever the highest number is, look there. And again, we go 1, 2, 3. We search in those pockets. Is it left? Is it middle? Right? Then we start searching. And again, we're reducing the number of hits that we need to find a record. So I've got some calculations. With 1 million records, if I'm looking for a key, if I'm looking for a value, statistically, in a table of 1 million records, statistically, for me to find a record that I want, in a table with no indexes, but 1 million records, I would go through, look. It could be the first, or it could be the last. So I've had one hit, or I've had 1 million hits. On average, I would do 500,000 hits to find a record. How fast does your processor work? Well, 500,000 may not take that long, but it depends on how many records you're searching, and all of a sudden you have time. In a table scan, in a binary search, this sort of search, if you have 1 million records, the formula is log 1 million divided by log 2, and if the binary tree is balanced, on average you would need to do 20 hits to find a record that you're looking for. And in a balanced tree, depending on how many leaves it has, 1, 2, 3, 4, and how many branches it has, it's log 1 million divided by log however many branches there are. And generally, 1 million records, to find a record, it's up between 5 and 9 hits. Bang, 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 got it. And then what the index does, it stores the key that you're looking for and the memory location where the data is. So it goes to the index, finds the field that you're looking for. There's the record, goes straight to the table to the location in memory, got it. That's how indexes work. Now, next. So the optimizer will do the calculations. Is it cheaper to do a table scan? Is it cheaper to do an index scan? Because index scans, even though they get the record quickly, you have to go to the index, then you have to go to the table. Bit expensive. Let me go back. So, what is an index? Is a schema object that exists primarily to enhance performance. Understanding and using indexes effectively is of paramount importance. I read that already. How are indexes implemented? Most large database systems use the B tree. B for balanced, not binary, to implement an index. B tree has a hierarchical tree structure. At the top is the header. This block contains, I'll show you all this sort of stuff. And the rows in the table are identified by their row IDs. Now, this is my very crude attempt of illustrating what a binary or what a balanced tree index looks like. So we have a header, and in a header we have 3 leaves or 3 fields, and those in the 3 fields I sort of know that the lowest number is going to be 1 and the highest number is going to be 90, so I divide it up from 1 to 30, 31 to 60, and 61 to 90. That's the key that I'm looking for, the value. It could be the surname, could be anything, but the values that are indexed. So I divide it up into 3, and then each one of those fields, it goes from 1 to 30. We divide it up into 1 to 10, 11 to 20, 21 to 20, so and so. Then from 1 to 10, we go through, and then we then break it down into 6 or 7 or whatever numbers that there are. So let's just say, for argument's sake, I'm looking for 27. Identify at 27. We always go to the header. We look, is it between 1 and 30? Yes. Then I go over here, there's a pointer, goes to another tree. Number 27, is it between 1 and 10? No. Is it between 11 and 20? No. Is it between 21 and 30? Yes. Then I will go into the leaf over there. I should have picked 9, because in 9 I would have said, oh, is it between 1 and 10? Yes. Go over here. Then we do a search one at a time at the index, and then we get the row ID of where the data is in the table. So we go through the index, we look for the value, bang to the table. And this is where we do the joins and so on. Okay, so that's your binary balanced tree indexes. This is how the database system implements indexes. And indexes, the selectivity of a column or group of columns is a common measure of the usefulness of an index on those columns. Indexes are selective if they have a large number of unique values of few duplicate values. Date of birth could be very selective, while gender would not be. So in your select statement, where you write a where statement, where date of birth is equal to blah, we might, if we are doing a search on the date of birth, we may very well index the column date of birth. But in the date of birth, if we had 1 million records, you know that there are going to be 365 unique values statistically out of the 1 million. So on each day, statistically, there are going to be so many records, so many people with that same date of birth, yeah? Is there going to be 365? Oh, but then the years as well. So 365 multiplied by the year ranges and so on. But the point I'm trying to make is that even if we index a column, potentially the system will sort the data out, and then there could be many values of the same value in the index. But at least we go through and we have a look. When we go into the index, we don't search one at a time. We sort of start, look at the top, look at the bottom. Go to the middle. Is it less than or equal to? Go there, and we find a record. Once we find the first data, we then look. So that's all cost, all cycles, all time. And then when we find whatever we need, bang, we go into the table and get the record. Okay, so index selectivity, that's what's meant by index selectivity. Now, if we have a primary key, the selectivity is 1. There is only one value in a primary key, and the system goes through, okay, I'm looking for a staff ID, bang, 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 got it. And that, then it goes into the foreign key or the joining table. The primary key has a foreign key. There will be many foreign keys to your primary key. But at least when we join the table, we found the record, information from the parent table. Then we can go through and then start looking at the records in the joining table. So for us to say select star from blah, 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 table 1, table 2, where, and you join, this is where, whether you look through the index or whether you look through the table scan, will determine the selectivity of your index, and the system will calculate out from the statistics that it has. A unique index is one that prevents any duplicate values for the column that make up the index. So if we have a situation of a unique index, that is a primary key or the identifier or something unique about that value, and generally primary key. If you remember your database fundamental days, remember we're talking about keys and we spoke about candidate keys. Remember? Now I spoke about this in class already. We choose one to be the primary key. So we say, okay, this column is a primary key. But then when we turn around and when we say, oh, this is a candidate key, which means another field can also be a primary key. But we chose to use this one and not that one. What the designer is telling us, that second key must also be unique. When we create a primary key on the table, we say primary key, enter, the system goes away, creates the table, and then it creates an index of the field that is the primary key. And of course, if we then try to put a duplicate value in, it's not that you're putting a duplicate value, it's that you're violating the index. And it goes, beep, value already exists. So we're not allowed to put two values in there. Right? We must have a unique value for the primary key. In our candidate key, that also has to be unique. But there's no such thing as saying, oh, candidate key. What we do is we create a unique index on that column, the developers. Because the designer told us this is a candidate key. That tells us that it has to be unique. So primary key, the system creates an index. Candidate key, we, the developer, will create a unique index on that field to prevent duplicates. Yeah? So this is how we use indexes in there. Non-unique indexes. A non-unique index can be created on a column that has duplicate values. So as many values as you like, but the trick with indexes is the system will then look at the data in effect will be ordered from the lowest to the highest or whatever the index controls. You'll hear concatenated index because we spoke about primary keys and whatever. We assume we've got one attribute. It could be that in our where statement, we are putting in a multiple where clauses, and if those where clauses are searching for certain parameters, we index those columns. Concatenated index, an index with more than one columns. So it could be surname, first name, date of birth. Those three columns would be indexed. And I think I have a slide to illustrate that. Creating an index, a syntax for creating an index, create index, whatever the index name is, on whatever the table is, in bracket, you list the columns that you want the index to be created. You can have multiple indexes on a table. You can have an index on each column if you want to. Remembering though that index could be expensive because every time data changes, the indexes have to change as well. Using an index, once the index is created, how do we use it? You don't have to do anything to use an index. From a developer's point of view, well, almost nothing. If an index exists on a table, the optimizer will decide whether it is cheaper to use the index or to do a full table scan. The optimizer will look at the where clause of your SQL statement. If the index columns appear in a where clause in the order that the index was created, then the probability of the index being used is good. So it's the probability. And here we have create index. We're giving an index name on an employee table, and we're creating a concatenated index on surname, first name, and date of birth. Then we write a SQL statement. Select star from employee where. Now note the order of my where statements. Where surname is equal to Benkovic, first name is Laurie, and the date of birth. The where clause is being written in the order that the columns are indexed. Modern database systems will analyze your query and say, oh, look, do we have an index in that order? Because you might write the query, date of birth first, surname is Benkovic, and first name is last, not in the order that the index is created. The optimizer may not recognize that it has an index for those fields, because it might recognize that it has, for surname. But the surname is a field at the start, but it's the where clause, so the calculations could be a little bit out. Note the order of the columns in the query is the same as the order of the columns in the index. This means that the query is a good candidate for the index to be used. So chances are that us using this index to find this record, statistically the computation of picking the value, how many elements are there, how many elements are there, and how many elements are in there, statistically we'll say the cost is blah using an index, and the cost is blah using a table scan. Index is 5, table scan is 50, I'll use an index. So then it finds the record and bang, it goes into the table to get the data. That's the optimizer. So, guidelines for concatenated index, create index, blah, blah, blah. So columns in a where clause, surname, first name, date of birth. So, you as a developer are writing or will be writing SQL statements against the data that you've created, whether it's for your program or whether it's for reports or requirements for the future because there's a business case to create something. So you have a vague idea of the sort of queries that will be executed against your table. From that design, you create a table, and then depending on the queries that you'll be using, or as time goes on, you will look at the sort of queries, the heavy queries, and you may very well create indexes to speed up your queries. Now, if we create an index on surname, first name, date of birth, and in our query, our where statement, we just use the date of birth or first name, then the index will, then the probability of using that index is low. So if we do create an index on surname, first name, last name, and then in our where clause we only use the first name, where first name like Laurie, then the cost of using because Laurie is the second field in my index, the cost of finding that in the index and then going into the table will probably be too expensive. Statistically, I'm saying. So the optimizer will look at the index, because when you create surname, if you can visualize it, visualize an index and a memory map where the system is putting all the surnames in an order, then within the surnames it's putting the first names in the order, and then within the first names it's putting the date of birth in the order. That's the order that the system creates. Then all of a sudden, surname will be in the first name, then the date of birth, and then some dummy developer turns around and says, well, date of birth is such and such, and then the index is over here, trying to find the date of birth, trying to work backwards would be very inefficient. So a developer, when they're writing SQL, when you go and get your first job and they get you to write a few reports, and then you're going to be modifying data, or they're going to say to you, look, this report is running 3 hours or 4 hours, it used to run a lot quicker. The first thing that you will do is you will look at the indexes on the table, and then you will look at your select statement, particularly the where clause. And then you'll see what's happened. How you wrote the query based on the indexes that are in the table. And what kills an index? Often you may create an index on a column only to find that the optimizer is not using the index because the wording of the SQL. Some situations that disable an index. So you've got a table, you've created an index, this is fantastic. Then you start writing your SQL statements and you find that the index is not being used. Some of the reasons are queries involving are not equals. When you say not equal, because you're trying to compare something in an index, but you're saying not equals. Index is killed. Searching for null values. Accidentally disabling an index with a function. And I have to tell you a story about my friend Danny, who worked at Origin Energy, who is the best developer that I've ever met in my life. And we were writing he was writing this super duper application, web-based application, and picking up data from Melbourne. And he wrote this massive SQL. It was a big thing, put it on a website. The ladies were using it, very happy. They pressed a button, the hourglass goes, bang, information comes in. Data's basically coming into the table. It's growing, it's growing, it's growing. All of a sudden, the hourglass is going. And Danny was one of the best performance tuning analysts that I've ever seen. He was unbelievable. But the hourglass is turning. Then eventually time's out, gone. What the hell's going on? Help desk comes in. Danny wrote the code. It can't be performance, it can't be anything. Anyway, it took us weeks to find it. So you see this thing, accidentally disable an index with a function. What Danny did, and he knew it because later on I've never seen anybody so embarrassed, is that he wrote the code, then of course he goes to the testers, and the testers test it, everything works okay. At the last minute, the user said, could we have a date in this format? So he put a toDate function on a date field, or can we have a date in this format? And he put a toDate function that I showed you, or toChar, on a particular date to format a date in a particular format. Simple change. There's no need, we'll just let it go through. It's all been tested, etc., etc. That toChar on an indexed column killed the index. And what he didn't do is he didn't check the explain plan, which I'll show you in a little while. And then what was happening is the index wasn't being used. Data volume was low, so the query was being executed. As the data volume grew and grew, the system was doing a full table scan instead of an index. But before, when he was testing and developing, he was looking at his queries, he was looking at his explain plan and everything. Yeah, beautiful, it works. One simple thing. And that's when I learned, and that was the best thing for me. Even the best of the best make mistakes. And you have no idea how good I felt after that. The best of the best. You just have to be careful. But when you're creating and when you're working with these environments, you have an index. You have to be aware of changes you make, how you write your queries to take advantage of the index, and then checking that your assumption is working. And I'll show you an explain plan. Queries involving not equals condition. Not using an index is generally a sensible approach. If we want to retrieve rows that are not equal to a set of values, then a full table scan may be the fastest way to retrieve the data. And I'm sorry, I didn't finish searching for null values, accidentally disabling an index with a function and using the like operator with a leading wildcard. You know where something like and then you put a percentage? If the percentage is the first thing, index kills. So if you have an index in that column that you're searching, you put that percentage character in there, gone. The system won't use the index because it doesn't know how. Searching for null values. So this is an example where I might write a query that says where, and I have an attribute on a table, and I put an upper on that attribute, and then I put an upper on something that I've passed in. Something that I've passed in, this is fine, but this is an attribute on a table. This will disable the index if I created the index on the postcode, on the locality table. Using a like operator with a wildcard. So this is an example of things that are being, index will be used, index will not be used because of this leading character, and so on. Hints, I won't talk about hints, but oh yes I will. Sometimes you'll see code that has this sort of information in there. Select, and then after the select statement, you'll see the C style / plus, and then you have a word in there. The word would be like, rule-based optimizer. This is, you are telling the optimizer or suggesting to the optimizer what to do. So hints are instructions to the optimizer that I would like you to do that. Yeah. This insert, so note on the insert, we are having an instruction that says append. Now this is very handy because you consider if we're inserting data into a table, what the system will do is it will go through and it will try to find a vacant, because you might delete records, so there's gaps all over the place. And the system may go through and search for a vacant space to put your record in. Oh yeah, bang. Look, bang. Look, yeah, bang. Find a record. This hint, append, says when you're inserting, always go to the end and put it in. Always go to the end and put it in. Yeah? Which is much quicker, but you're using all that space. So this is this slide sort of shows hints. And when you talk about hints with the optimizer, with this / and a plus, you're giving some instructions to the optimizer to, do something, do a table scan, use an index, don't use an index, etc., etc. And if you Google it, you'll find that there's a lot and lots and lots and lots and lots of different hints that you can give to the optimizer. And when you go through and you start doing this stuff, and if you ever do get in, well, you will get involved if you work in a database environment, and you're writing code, and if you optimize as, it's not doing something that you think should be done, you go through and you can suggest to the optimizer through those hints. And if you're looking at code, if you see these sort of things, they are not comments. What makes it a non-comment is this plus, because if it was just a / multiplication / something would be commented out. This plus is basically telling it it's a hint. So if you see code like this, leave it alone. That's an instruction for the optimizer. It's not something, I'll clean this thing out. It's not a comment. It's an instruction not an instruction, it's a hint for the optimizer. How can I know what decisions the optimizer will make? Most database vendors provide tools to enable you to tune your SQL statements. The most common tool is the explain plan. Now, before the database server can execute a SQL statement, the statement must first be passed to develop an execution plan. The execution plan is a task list that decomposes potentially complex SQL operations into a series of basic... look, you can read this yourself, but what I want to do is I want to show you this. Here is a statement, a select statement. I run it, yeah? And which is what you're basically doing. I run this and it processes. Did you note there was a delay? Did you note the delay? Anybody notice? Not much, but it was a little bit. Watch when I execute it again. Yeah, execute it again. Now, believe it or not, it's much quicker. Why? Because the very first time that your SQL statement gets executed, it goes through the execution plan. It does its calculations. Yeah? And what it does, the system puts it away and says, I'm going to remember this because if this SQL statement gets executed again, I'm going to go into my execution plan and I'm going to know how I'm going to execute it. As soon as I change something, see the delay? Watch. Yeah? Oh, could you tell? Yeah, but there is a little bit of a delay because I changed something and it looked what was stored. It said, oh, it's different. I have to now calculate a new execution plan. If I now go back and change it to 1 and I execute this, because it already remembers it. So this is something else that you remember. If you're changing your SQL statement a lot, particularly with dynamic SQL and so, the optimizer has a little bit of a lag. But that's not what I wanted to show you. When you're writing SQL statements, there's a little thing up here called explain plan. See that? And now what happens, this is when I talk about an explain plan, in the slides, I'm talking about how do I know what decision the optimizer will make. We talk about an explain plan. Yeah, so now I'm coming into the database and the way that we could test to see how the query is going to run is we could write a query, execute it and put a stopwatch on it and time it. Now that might take hours. Then we change the query, maybe the order of the table, maybe create some indexes, then execute it again and put a stopwatch on it. The one that's the quickest is the one that we're going to take. But we're going to try different combinations because we don't know exactly what the optimizer is going to do. We've got to put an index in. But what's the optimizer doing? How do I know what the optimizer is doing? There's this thing called an explain plan. SQL Developer is a free tool, so you get what you pay for. But here we have an explain plan. And what this thing does is it goes through and basically tells you the execution plan of that SQL statement. And it gives you a cost. 77. Now, if you're running those monster queries that I showed you at the week 1 and week 2, you will find, and particularly if you're joining a lot of tables and massive amount of data, you will see these values are in the millions. And what you do, what the developers do, what we do, what you will be doing if you're working in this sort of environment is you will be writing your query and you will be using a tool like this explain plan, and then you will be creating indexes. You will be dropping indexes. You will be changing your SQL statement by the way that you order your tables, the way that you create your where statements, and you will be checking each iteration of it to see what's the cost. And then you are always looking for the cheapest cost. Because what's happening here, this cost or this explain plan is I'm asking the optimizer to tell me what it's going to do. The SQL statement that I give it, you say, optimizer, what are you going to do? Because what the optimizer does is when it runs this SQL statement, it basically goes through and does a combination, does a calculation of the combinations and picks the cheapest one. So here, what time is it? I haven't got time to create indexes. We might do it in a tutorial if we get a chance. if I were to create an index, will the index be used? And then maybe disabling the index and so on. So if I might create an index, then I would go through the execution plan. In a dummy donkey world, we would write a SQL statement, execute it, and time it. So any changes that you make, time. Oh, okay, I've got an efficient SQL statement. But again, it could change over time. And we don't want to time it all the time because that means executing the data. What the execution plan is, or what the optimizer does, statistically, it does the mathematics and works out from the statistics of your data and a spread of the data, indexes and so on, what's the cost of the execution. Yeah, so that's the explain plan. If I ask you in the exam, what is an explain plan? And again, as I say, when we change the query or change the table names or the order or whatever we do, create an index, drop tables and so on. So we do an execution plan. And like I say, our data, in our database, even though the transaction table's got, 40,000 records, no, we can't stress it. But when you're working in databases that have millions of tables and you're joining onto millions of records, then you all of a sudden realise that this is not a game. Particularly when your code is running to produce a report and you might write a SQL statement that'll take 2, 3, 4 days to run, and they want it in an hour. And you say, well, it's impossible, I can't do it. Then you turn around and you start working at different ways of doing it. Okay, they're looking at only this year's data. They want a report for this year. What I'll do during the night is I'll create a little routine that'll just export the 1 year's data into a table so my base tables are much lower. So this is basically then you forming your plan of how am I going to bring my report down to 10 minutes, 5 minutes, whatever, when you're talking at large volumes of data. So this performance tuning has got many, many, many horns on it. But what I'm talking to you about is basically SQL statements and a single SQL statement. Explain again. This is you can read this at your leisure. But before we had tools like SQL Developer, SQL Developer, whatever, we used to have to rely on manual tables, and that sort of tells you how to create an explain plan table. And this is what I just showed you in SQL Developer. Toad has a graphic representation where it basically lists the tables down, and then you see it. You're watching how it all executes and how the data bubbles up and so on. Now, I'm running out of time, but there's one thing that I want to talk about and I don't want to forget. Because we have a situation where we have programmers that are writing code. Now, the programmers in here for the assignment will write code that will write at various times. And then you will probably walk away from this lecture thinking, oh, well, how do I do an explain plan on my code? My lecture is not about a programmer developing efficient code. Now, there's a student in this class that I may embarrass. And if I do embarrass you, I apologise. I really apologise. My intention is not to embarrass you, but my intention is to show people how some people think. This student came to me and said, what do you think I should do, Laura? I gave him that cursor where they go through and pick up the transactions for a merchant. But I said there's a little fly in the ointment because there's a minimum amount there. So this student came to me and he said, oh, well, do you think every time I loop around, I should write a little routine that goes and checks the minimum amount? Yeah? And I said, why the hell would you do that? Well, I have to know what the minimum amount is. So this fellow, or girl, right, basically in their mind, they had the SQL statement that I gave them, which is merchant ID, total amount, whatever. I said, well, now you have to check for the minimum. In their loop, they were going to go hit the database every time and check the minimum amount. Now I see some of you smiling, but half of you will do something like this. Then you think that you have to ask yourself, how often will that minimum amount change? Answer is, for never. And why the bloody hell would you hit the database every time that you're looping through a record which you're going to write to a table to check whether you're going to process it or not. Doesn't it make more sense to do that SQL statement once? Even better, doesn't it make more sense that when you write that SQL statement, you include the FFS reference table and get the minimum amount, and sure, it's going to go against every column, but you're hitting one bit to the database. Now, most of the programmers, young programmers, think like, oh, every loop I have to go through and hit the database. That is expensive. Doesn't matter how efficient your SQL statement is, if you're doing stupid things like that, you are putting processing time on your code. And these are the people, because every time I mark, every year without exception, I press enter, and the first thing I look at is how long it takes. And most of them go, boop, boop, done. With a little bit of luck, I might set something up, and then I'll show you how I mark before we finish the year. And then I'll see, press enter, then I'll see, warning, 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 shit programmer. Yeah, I make no excuse for saying it. And then I see this happen. And I go through the checker, yeah, because for them, syntactically, it all works. But they're not thinking about what's happening and how many processing cycles you're doing, how many hits you're doing to the database. And then those ones where we turn around and press enter, and then it comes back. So don't want to have a look at this thing. Did I tell you about that lady when we started the class, where I gave an assignment about Helen's data? Now I think I sort of told a story where there might have been 200, 300, 400 lines of code to solve another assignment. This lady, and a code would run under a second. This lady wrote some code, and she would have had thousands of lines of code, and the program ran for 4 hours, and then I killed it. Now, you think about enter, and it finishes, so a reasonably competent student, sub-second. 4 hours her code took, and I killed it. And she was devastated because I failed her. I said, look, this is ridiculous. And as far as she was concerned, her program was perfectly okay, and she had no consideration about how long it took. But she was an idiot programmer. She would go through and go into the day, check this, loop around, do all this sort of stuff when you're getting into something directly. Now, this is not performance tuning in the database. I'm talking to you as developers. So now, in my tutorial solution today, for the guys that were in my class, and please go online and listen to the tutorial, that is an extremely inefficient solution. I told my class, the tutorial class, I created the tutorial solution to illustrate to you how to reference the elements of a collection. But I stress that it's an extremely inefficient solution, because the SQL is fine. I loop around, I populate some arrays, then I loop around again, and I populate the sum values, then I loop around again and do something else. And here, with the data volumes that we have to finish this sub-second, you don't see a problem. But if that code was released into production where the data volumes will grow quickly, that code will die in a matter of weeks. Just overloaded, not because it is bad, it's just inefficient. What I should have done in my solution is I should have, in my one SQL statement, bought everything from the database in one go. Now, I haven't got time now, but I'll show you, I'll put on UTS Online one example of me with that cursor where I'm picking up the settlement amount for each merchant, where I'm picking up the minimum amount as well. Yeah? I'll show you, not that I expect you to do it, but to illustrate to you. Yeah, so for each record, the minimum amount is there. I don't have to go somewhere else and look. I don't have to store it anywhere. I'm doing it all in SQL. Yeah? Now that SQL, performance tuning, is I'm talking about SQL. Yeah? But now, at the moment, I'm talking to you as developers with performance. And then you guys have to be aware, most of you have to be aware that you are very, very inefficient programmers. You be aware, then you can do something about it. Programming is not about syntax. Efficient programming, I should say. It's not about syntax. Efficient programming is about thinking what you're doing and minimizing your hits to the database and processing whatever. Okay, so I think, how do we go into the global temporary tables? Look, I won't. There's this thing called temporary tables in a database where we can go through and create temporary tables as we go in through and processing data, and the system automatically cleans up those temporary tables. But you can read this at your leisure. You can Google. Please do yourself a favour and Google Explain Plan and Efficient SQL or Performance Tuning SQL. You will see that this is a friggin' career in itself, and you would be wise to have that in your back pocket, not as being an expert, but as a reference, because when you go for your interview, I guarantee they're going to ask you about performance. They'll probably feel you out because you're a graduate. But every job, and even have a look at the jobs that they advertise, I think they still do it. If you see for a database developer, they'll all mention performance. And what they're talking about is this, not you being an efficient programmer, it's performance, writing SQL, understanding indexes, understanding how the execution plan works, understanding how to analyze your SQL, etc., etc., etc. So, if nothing else, put it into your, as part of this little exercise. Most of you don't do your tutorials, I've seen that, but spend that 15-20 minutes and just Google SQL performance. And just put that in the back of your mind because, it's very important. And that also goes if you're a Java developer, because if you're a Java developer, you will be writing your SQL probably at the client side. And that SQL has to be executed. And even if you do write your SQL on the client side for your Java, for your web application, you need to test that in the database, and then you should go through and do an explain plan, particularly if you're interrogating large volumes of data. Anyway, that's all I've got to say. Enough lecturing. Oh, hang on. No, it's not enough lecturing. I'm a lecturer. I'm supposed to lecture. But, I'm not your parent. I don't have to friggin' do this and do that. So thank you very much for your patience. I hope you got something out of it. From now on, the tutorials are going to be very sparse, because to do a tutorial on something like this, I can't, because I don't have the data volumes. I've got nothing to illustrate to you.
In the tutorial, are we able to present you with a problem in our code and then just ask for
definitely, and I'll definitely give you my opinion.
Right.
But you have to understand there is not one answer.
Yeah, fair. I think it's more just a point in the right direction.
Oh, look, I'm more than, I welcome it. I even welcome you putting it on UTS Online.
Yeah.
Sorry? No,
You
that's
don't
it.
have to put code on UTS Online, right?
Well, don't give away your good stuff. But send me an email. Like if you want to keep your code to yourself, send me an email. Something doesn't happen, something doesn't work. I'll tell you, look, you've done. But because from now on the tutorials are going to be sparse. Next week we've got administration, and I'll show you the magic of how we make tables transparent and where they are and all that stuff. How the hell do you do a tutorial on that? So I'll be sitting there, and you can ask me all the questions that you like if you and your other tutors. Fahime's class comes in with me, so that's. But if you're in Al's class, sorry. Well, they're all here. This is the lecture, so they should all know. If they're not here, bad luck. So as I say, the tutorials are going to be a little bit sparse. I'll certainly talk about performance, and I might just go through and enhance on this explain plan. But as I say, I don't have the data to test the system. Even 100,000 records is nothing on a laptop. Even imagine a big Unix server or whatever. So, we're talking about tables with millions of records against millions of records, and you multiply a million by a million when you join it, then you start getting the stress tests, and again, it's you guys are thinking syntax. Oh shit, I can't get my SQL to work, and your main concern is syntax, but you should be starting to think about what the way you write your SQLs, your indexes, the performance of your SQL statements, because that's a very, very important issue. What happens when a query runs? And then have a look at that explain plan. See what the system's doing. See what a hash join is and how the optimizer executes the code. For your own education, more than anything, I'll ask a question: what's a rule-based optimizer? What's a cost-based optimizer? Some of you will say, what's an optimizer? Well, but what's the difference between a rule-based, cost-based? I might ask you, what's an explain plan in the exam? Just basically read your lecture notes. All right, thank you. See you next week. Stop recording.